the shoulder of giants. Led Zeppelin. Hey, put my guitar away. Today, I'm going to demonstrate rolling without slipping, and that would be this pool ball, number 10 ball, placing it on a surface, and you'll notice that it's rolling without slipping. So it's exhibiting both translational motion and rotational motion all in one. Now, in order to solve for either the angular acceleration of the rolling aspect or the linear acceleration for the translational aspect, we have to use both Newton's second law and its angular equivalent. We're going to couple those expressions together and solve for the linear acceleration of the pool ball. In order to do that, to couple these two together, I have to apply my magic substitution, alpha equals a over r. Now here's the challenge. So I don't directly ask for the linear acceleration, but I think you're going to have to decide, oh, we need to calculate that first or derive that first. Here's the challenge. Predict the time it takes for the pool ball to travel 1.1 meters down a 5-degree inclined plane. Now, here's the predicted time, so I'm going to give it to you. But in thinking about that, okay, if I know the distance from here to here, which is 1.1 meters, I got to predict the time. Second basic kinematic equation. I need to determine the acceleration. Now, I determine the acceleration through the coupling of the Newton's second law and its angular equivalent. So let's get after it. Okay, every problem starts with a sketch or a diagram. So here's our diagram, and I massively mess diagrams up, especially when it comes to free body diagrams. So please don't be too critical, but I'm going to show you all the vectors acting on the ball as it rolls down the inclined plane without slipping. All right, one of my favorite vectors to apply is mg. I think everybody identifies mg, and that's the force acting on the ball more or less straight down. So there's mg. Now that you've been told, don't put the components on the diagram, but I'm going to do it anyway, just so that you see that there is a component of mg down the inclined plane, and there's a component of mg into the inclined plane. Good old mg sine theta and mg cosine theta, which we're going to relate to, I think, we're going to relate to the friction force, but maybe not. Maybe not have to, but I'm going to put it on there anyway. The normal force. Okay, that's a vector you can add to the free body diagram, but never, ever add these components when you solve problems, especially with physics professors that are really picky. Now, what allows this ball to roll without slipping down the inclined plane is the friction force. Okay, if I were to push this down the inclined plane, the friction force always acts opposite the motion. So I'm going to label a friction force between the ball and the surface. And incidentally, folks, that friction force applied here between the ball and the surface to the axis of rotation, that constitutes a torque, and that's technically what gets this thing rolling, okay, without slipping. So the distance from the axis of rotation to the point of application of the friction force, okay, constitutes the torque. Okay, so we're going to identify the torque over here in the angular equivalent of Newton's second law. All right, let's start by formulating an expression using Newton's second law. How many forces are acting along the line of action? Yes, two. There's one down the inclined plane, mg sine theta, and there's one up the inclined plane along the line of action, and that's equal to ma. Okay? See that? All right, next up, we have to apply the sum of the torques equals I alpha. All right, how many torques are acting on that ball as it rolls down the inclined plane without slipping? Okay. Identify the force that actually gets it turning, and that would be the friction force. So there's only one torque. Some people think this mg sine theta is pivoting the ball in contact with the inclined plane. I get that, but it's actually this friction force that's supplying the torque. Now, is that a counterclockwise torque or a clockwise torque? Okay. R cross F, thumb into the board. That's a negative torque technically. So that's a clockwise torque. So I'm going to show that as minus R cross F of that. And I'm just going to put the cross product thing there just so you know that R is perpendicular to the friction force. And then the angular acceleration is negative as well. Okay, because it yields a clockwise angular acceleration, and by convention that's negative as well. And they're going to cancel because you got a negative on both sides. But I always want to be consistent in case we have another torque, counter torque, clockwise torque, what a counterclockwise torque. Hey, you never know. Now, to merge these two expressions together, I'm going to solve for the friction force with the Newton's second law part. Okay. So we have mg sine theta minus ma, and then I'm going to substitute f of f into our angular equivalent expression for Newton's second law. So we have r times mg sine theta minus ma is equal to I alpha. Now, at this point, I'm going to substitute what I is. Okay, I for a solid sphere is 2/5 m r squared, and alpha a over r. Now, a over little r, we have big R. So here's a warning to everyone. If the distance from the axis of rotation to the point of application, okay, is not equal to the radius of the rigid body that's rolling without slipping, don't get those mixed up. They're not the same. But in this case, the distance from the point of application to the axis of rotation is equal to the R of the rigid body. So we're good. We're going to be able to cancel stuff. Okay. So that's going to be A over big R because little r equals big R in this case. But don't always assume that. All right, now we're going to cancel stuff. Okay, mass cancels. I always cry when I go to the extent of calculating rotational inertia. It's like, I didn't need to do that because mass cancels. We can cancel one R and another R. Boy, what a mess. Let's clean it up. So g sine theta minus a is equal to 2/5 a. Therefore, a is equal to, I'm gonna go a little fast this time because I just don't want to make this video too long. A is equal to 5/7 g sine theta. All right. Now, if you substitute g, fundamental constant, 9.8, and theta, 5 degrees, out pops an acceleration. I don't know if you can see that. Hopefully you can. 0.61 meters per second squared. Okay, so that's my linear acceleration of this sphere rolling down the inclined plane. Hey, I had this thought. I knew I was going to bite off more than I can chew. But for you folks out there that have a video analysis feature, go ahead, why don't you tag that ball as it moves down the inclined plane and see if you come up with an acceleration of 0.61 meters per second squared. Could be a fun activity. Extra credit. Hey. All right. Now, what do you do with that linear acceleration? Well, I'm going to erase the board. Okay, I'll stand back here so you can take a look at it. Maybe freeze the reaction, and I'm going to erase all this stuff except for the acceleration. And now we have to predict the time it takes to go from point A to point B. Okay, notice I have some T lights, some nifty T lights. Again, if you need a reference as we roll this ball down the inclined plane. And it's a distance of 1.1 meters. And if I think about this, there is a basic kinematic equation. I call it the third one. I number them for my students. So x is equal to 1/2 at squared. All right, so that's assuming it starts from zero position, zero velocity, moves through a distance x, and a particular time t, given an acceleration. So solving for t, we get the square root of 2x over a. And if you plug in 1.1 twice 1.1 divided by 0.61, take square root, out pops 1.90 seconds. Okay, if you remember last time, I used my cell phone to determine the actual time. And now I'm going to be subject to reaction time because it goes kind of on the fast side. Watch this. So if I start my and then stop it, it's moving quick. So I'm gonna try my best. Okay, 1.9 seconds is the predicted, and here comes the actual. Are you ready? Okay. They say that we're good within 1/10 of a second. That's just first time around. 1.71. You're good within 1/10 of a second from the start and 10 seconds from the finish. Ooh. That's not that bad, as my father would say. Okay, I'm going to reset it and try again. I'm not going to fake it. I'm going to try my best to start it as soon as it moves and stop it as soon as it crosses the finish line. And I got 1.8 seconds. So reaction time, it's not the greatest, but it's PDC, pretty darn close. Now to finish this video, okay, let me go grab the ball. I have an extra credit item for you. Okay, here's the extra credit. If you notice in my diagram, go ahead and blow it up. I show a sandbox below the end of the board. And the distance from the end of the board, the height, to the sand bed level is 0.89 meters. So here's your extra credit. The distance, and I'll tell you a little bit. I want you to predict the downrange distance from the moment it leaves the end of the board. So that's your extra credit. Calculate Rx. Okay? Now I am going to do a little production here, post-production. I'm going to add a video clip of the ball rolling down the inclined plane and then into a box of sand, just so that you see it. You can only hear it, I think. I'm just going to let it roll down the inclined plane. Whoa, okay. Let me tilt a little bit. It's going to roll down the inclined plane. And if you heard that thud, that's it entering the sandbox. So you'll see a video of that. All right. The total distance that it's going to travel down the board. Okay, so for the extra credit, you need to know that. This is going to travel a total distance of 1.56 meters, as opposed to the 1.1 meters. All right, that's extra credit number one, because I have a second one. Okay. Use conservation of energy to predict the time it takes to go from start to finish through a distance of 1.1 meters. Use conservation of energy. Now, report both in the comment section. If you're somehow able to email me and you want to take a picture or create a PDF of your solution, I'll be glad to view it, grade it. Hey, I'm here for you. All right, I'm gonna go pick up my guitar and do my outro. I hope this didn't take too long. I told you I may have bit off more than I can chew. Okay, I entered with Led Zeppelin, and now I'm gonna exit with Beatles.